All right. Good evening, everyone. Welcome to today's JUPEB math class. This is week 11 of our math lecture series, and today we're going to be looking at ordinary differential equations, also known as ODEs for short. Please kindly indicate if you can hear me and you can also see my screen. Hello. Please, if you can hear me and you can see my screen, please kindly indicate so that I know that I am audible.
Yes, sir, we can see your screen.
All right. Wonderful. Thank you, Chibiki. So, without further ado, let us get right into it. So, today's class is going to be on ordinary differential equations, ODEs, like I have said. And our objectives for this lesson are to, firstly, identify ODEs in their different shapes, sizes, and forms. So, we have different types of ODEs, which are classified based on how they are solved. So, first objective, solve first order ODEs. So these include separable, homogeneous, linear, and Bernoulli equation ODEs. So all these are different types of differential equations and the different methods for solving each one of them. We'll also look at second order ODEs with constant coefficients, and then also look at the methods involved in solving. And then we are also going to look at real life applications. So applying ODEs to model growth, decay, and equations of motion. So these are the objectives for this lesson from the beginning. Hopefully we'll be able to go through the whole lesson outline, and by the end of the class, we should have achieved most, if not all, of what we set out to do from the beginning. All right, so we'll get right into it. And then the first thing we're going to be looking at are separable equations. So I'm sure by now we should be able to identify what a differential equation looks like, right? So we are starting with first order differential equations. Now, what are first order differential equations? So, of course, if you see a differential equation, you should be able to identify it, right? Because it's going to have differentials in it by virtue of the name. So it's going to have dy dx, right? Because that's a differential. So it involves a dependent variable and an independent variable, right? So if in this case now we have dy dx, it means that our equation is going to have x variables and y variables. Now the dependent variable is the one that the answer to it depends on another variable. So for example, in the case of dy dx, we see that what your x is going to determine what your y is. But then your x already exists on its own, right? So in this case, your y is the dependent variable, and then your x is the independent variable, right? So having established that there are dependent variables, so a differential equation can only have one independent variable, but it can have different dependent variables. So the next thing, what led me to talk about this now is identifying the order of a differential equation. So we are in this outline, we're going to be looking at first order differential equations and second order differential equations. Now, how do you know the order of a differential equation? You know that by looking at the differential coefficients, right? So the dy dx now is differential, and looking at the order. So the order is like, or the power in a sense, another word for it, power. So in this equation now, for example, in this example, dy dx is equal to x over y. So the power of the dy dx here is what? 1. But of course, n raised to the power 1 is that thing. So which is why we say that this is a first order differential equation. Now, if you had something like d squared y over dx squared, then that would be a second order differential equation. If you had d cubed y over dx cubed, that would be a third order differential equation because the differential is raised to the power 3. The differential is raised to the power 4 to be a fourth order differential equation, and so on and so forth. So basically, what determines the order of the differential equation is the order of the differential coefficient of the highest differential coefficient appeared in. Now, you can have more than one differential as well, right? So you can have something like dy dx plus 2 d squared y dx squared plus d cube y dx cube. Now, the order of the equation of the differential equation is determined by the order of the highest differential. So if you have order 1 differential, order 2 differential, order 3 differential, the order of the equation in general is a third order differential equation because we're going to consider what's the highest differential that I
I'm
have
not seeing your
in
screen.
this equation.
I'm not seeing your
Hello,
screen.
you can't
Hello,
see
I'm
the
not seeing your
screen. Is that does that go for everybody? Or
I'm
it's
seeing it now.
just okay? It was probably a network issue from your end because I haven't moved the screen. So then to my point I was making is that our differential equation takes the order of the highest differential in our on our ODE, right? So if you have order 1 and order 3 differentials, the order of differential equation is not order differential equation. But for the purpose of this lesson, we're going to only deal with first order and second order differential equations. As you go further than second order, equation starts to get very complex, and then solutions to those kinds of equations are beyond the scope of what you're supposed to be looking at. So we're only going to be considering first order differential equations and second order differential equations, right? Now, for first order differential equations, which we are going to be looking at first, unintended, we are going to be looking at 4 different methods by which we can solve these equations, right? 4 different methods where we can solve first order equations. So we're going to look at first order first, and then we'll now go and look at second order differential equations, and then we look at applications. So the first type of equation we are considering for first order is separable equation, right? So we're starting with a separable equation. Now, separable equation is a type of equation where it is possible to get all the functions of x. So like I said from the beginning, there are 2 variables, right? One is x and one is y. Now, for a separable equation, for an equation to be considered separable, it is an equation is separable. It is possible to get all the functions of x and dx to one side and all the functions of y and dy to the other side. If you can do this, then that equation is separable, and then you can now follow the method for solving separable equations to find the solution to that differential equation. And when we say find the solution, basically we are saying, integrate it, right, and solve it, and then get an answer. That is solving differential equation, right? Now, how do you determine this? Of course, normal change of subject. So you treat it like an equation, do your normal change of subject. If you can separate it, then you go ahead to solve. And this is one of the easiest methods of solving. So the first example we have here is dy dx is equal to x over y, right? So y dx is equal to x over y. Now, is it possible to separate it? Meaning, is it possible to bring all the x and the dx to one side and all the y and the y to one side? So we tried, and we see that it's possible because by simply cross multiplying, what we have here is that y dy is equal to x dx. Now, at this stage where we are, we clearly see that all the y terms are on one side, including dy, and all the x terms are on one side, including dx. Once you can achieve this, you have separable equation. And now what do? You simply go ahead to integrate, because remember we're trying to solve it, we're trying to eliminate the differential. And to do that, we have to integrate. So you now integrate both sides, right? So you integrate this side with respect to y, you integrate this left-hand side with respect to y, and then integrate the right-hand side with respect to x. Now, last week we had the class on integration. So if you're in that class, you should be able to at this time know and be able to perform integrations of simple functions like this. So for example, when we want to integrate y now with respect to y, it's simply going to be y squared over 2. Of course, following the simple formula of integrating with the power. So y raised to power 1 plus 1 over 1 plus 1, which is y squared over 2. And then the differential disappears, right? Now that's equal to, then I do the same thing for the right hand side, x squared over 2. And then of course, as usual, when we perform an integration, always add the constant. Always add a constant. So that's going to be plus c. Now that you have eliminated differentials, this solution to your differential equation. Because you can go ahead to make y the formula of whatever and equate to this principle. The point is you now have a normal equation, not a differential equation, and a linear equation. And so you have been able to arrive at the solution to it. Now, another example is given here. The y dx is equal to exponential x exponential y. Now, of course, we try again to get all the terms of x to one side and all the terms of y to one side. And it's possible to do so, as you can see here. So e exponential minus y dy is equal to x, and of course, we integrate this. Of course, last week as well, I also mentioned and shared an integration sheet. So you should be able to also make references to this and check for integrations of common expressions such as exponential x or ln x or log x or cos x. All these common algebraic functions are common. Their integrals are usually always the same. So making reference to a cheat sheet like that should be able to give you or recall to memory what integration and so what is the differentiation of this common term. And then if you solve them as much examples as possible, you will not be able to get familiar with them and then know when to use which. So having separated this equation now here, we now integrate both sides as usual. And then integration of exponential x is exponential x. Integration of exponential minus y is going to be exponential minus y, of course, with the minus sign now at the bottom. And then we always add the constant plus c. And we have the solution to our differential equation. So this is a rundown of how we handle separable equations. Pretty straightforward. It's the easiest method, easiest form of or easiest set of solutions to a differential equation that you can come across. So you always check first, see, can this equation be created? If it can, then you apply a method for solving the equation, which is simply integrating both sides and then have the answer to your differential equation. Right. So moving on, we go into the next form of first order differential equations. Like I said, we're working on first order differential equations. And having looked at separable equations, we're going to move into the next one, which is homogeneous equations. Right? Homogeneous equations. So differential equation is said to be homogeneous if it can be put in the form f of y over f of y over x. Right? So what do we mean like that? What do we mean by that? So where f of xy and f1 of x1, f2 of xy are homogeneous function of the same degree in x and y. So I would use a very simple example to illustrate what that means. Right? So what this is saying, so first of all, you apply this when you have tried to separate the variables and you see that it's not possible. So a quick example we can use to show this is And this example one, we have dy dx is equal to x plus y over x minus y, right? Okay, Chibike. So separating the variables, so Chibike asked a question in the chat for those that didn't see. So separating the variables is simply just, I mean, we all know how to do change of selector formula now. So it's just trying to see if it's possible to take all the y to one side and take all the x to one side. There's nothing really complicated. So for example, here now where we have dy dx equals x over y. If I decide to cross multiply, I have y dy equals x. So all the y is on one side here, and then all the x is on one side here. Once I can achieve that, I have separated the equation. In this one now, divide the x exponential x exponential y. If I cross multiply, so I bring the x over to this place, then the x and exponential x is here, and I now divide through by exponential y. So exponential y is now here, and then it can come up to the exponential minus y. So all the y is on one side, and then all the x is on one side. So it's just manipulating the equation. There's no rule, right? You just have to try and see if it's possible to get all the x to one side and then get all the y to one side. Once you can do that, once you have achieved that, then you can now go ahead to integrate both sides. So of course, you need to practice, right? I always say this, you need to solve as many examples as possible. You need to make out the time to do, repeat it over and over again, because that's the only way it's going to stick. It's going to now become muscle memory. And then when you ask the equation, it's not easier for you to solve it.
Hello, sir. Sir, I have a question.
Okay, go ahead.
Sorry, sir. Well, this under the previous one that you showed, example 2, sir. How can we differentiate the negative that y carries with s, sir?
How can we differentiate the what? Sorry, I didn't get your question. Is it Emmanuel? Hello? Hello?
Hello, sir.
Yeah,
What do you
were
mean
you,
that how
are you,
can we differentiate the minus or negative minus y?
yeah, so like I said, differentiation has been covered is under week 9's outline. So I don't know, we should we be going to cover differentiation again? It's assumed by now that you know how to do differentiation, but I don't know. Let me see. So this is you use chain rule, right? Like okay, so Chibiki, have you gone through differentiation before? Hello, Chibiki.
So can I hear you now?
Yeah. So I said, have you gone through differentiation before? Have you come across it before? Have you solved examples on it? Have you done it before now?
No, sir. No, sir. I missed the last class, so I didn't.
Yeah. So I if I decide to go into that now, it's going to extend our take out time for what we should actually be doing. But I think there are recordings for those classes. The last class was integration. Then in the course outline, the last two classes, the course outline is differentiation. So these topics should have been covered. And if you are not present at the class, then it will now mean we'll have to start going back to explain this concept again. But then I advise that you watch the recordings. I think those sessions were recorded, so you just watch the recordings and then try and see if you can follow up with what stuff then. But then is it just this? Is it just the minus you have a problem with, or generally you don't understand how you do the differentiation?
The problem I know that this differentiation there's formula they used to use and do this thing, but I forgot the
Yes.
formula. But is it the same formula with the difference of two square that you are using?
Oh no. No. So those are two different things. Those are two different things entirely.
Okay, maybe can list me out the formula. Can you? I just apply the formula and know how to solve it.
All right. So let's just proceed with the class first of all, and then if we have time at the end, I will come back to that because, like I said, it's going to be a derailing of our class, right? So it's not as straightforward as you're expecting. There are many different techniques and um steps applied in doing differentiation. What I will do is to share a cheat sheet for you, something that gives you like a very brief. Let me see if I can find something now online. All right, so let's just continue the class, and then I'll at the end of the class I will handle your question. Should be good. So
Okay, no
we're looking
problem, sir.
at
Thank you.
homogeneous. All right, we're looking at homogeneous equations. So homogeneous equations, I was saying before that. So here we're considering equations where we have tried to use separation method. We have tried the separation, taking all the y terms to one side and then all the um x terms to one side, and then it is not possible. So we now apply the method to solving homogeneous equations, right? So in this case, we are applying a different technique, right? Now we make a substitution. So we say let y equal to vx. Now, when we say let y equal to vx, we are now going to differentiate this equation y equal to vx. So if we have dy dx, right? Now dy and y and x are variables, and x and v is a constant. So we're going to treat v like it's a constant term. So dy dx is equal to, so differentiate v. So this is product rule for, yeah, and I'm making a lot of references to things that we should already know. So I hope that it's going to make sense in the end. So when you are differentiating and you have two terms that are multiplying each other, that's product. Two terms that are multiplying each other, you use product rule. So what does product rule say? Product rule say that it says that you keep one constant and then differentiate the other one. And then you now keep the other one constant and then differentiate the other one and then add both of them. So for example now, if we keep v constant and differentiate x, we differentiate x with respect to x, we have 1. So that's going to be v times 1, which is 1, plus if you keep x constant and then differentiate v, you're going to have dv dx. Since v is a constant term, so you're going to have x with dv dx. So the addition of both of them now is your final outcome. So dy dx is equal to v plus x dv dx. Now, these two things that we have, y equal to vx and dy dx is equal to v plus x dv dx, you would use both of them to substitute in your differential equation. And that's how this method works. You substitute y for this. Anyway, you see y, you put vx. Then anyway, you see dy dx, you put v plus x dv dx. Now, in doing this, you eliminate what? Y totally. Now, when you do this, you now solve your equation normally, right? And then sorry, can you hear me?
Yeah, you can hear you now.
Okay, sorry, I think I went off for a while. So when you now do this, you now solve the equation normally, and then you will now arrive to a point where you now get the final answer, and your final answer is going to have only v and x in it. Then you now substitute back v. So if y is equal to vx, then v is equal to what? Y over x. So you now replace back v with your y and x. You have your final answer. Now, the point of making this substitution is that because you cannot separate y and x normally as they are, when you now make this substitution, it's going to now make it possible for you to now have a separable equation, right? So this substitution enables you to make the equation separable. So now you're separating it to v and x, right? Because you have now made this substitution, it's now possible for you to make your homogeneous equation into a separable equation. Now, once you separate it, you're going to have v, all the v terms on one side and all the x terms on one side. And then you now integrate both sides. Please turn off your mic. I'm getting a feedback from my end. Once you are now able to separate them, you can now, like we did in this previous one, integrate both sides. Once you integrate both sides, you now get your final equation. Now, your final equation, like I've said, for it to be in terms of v and x. But then your original equation did not have v. So you now reverse the substitution you did, right? So where you now have v, you now replace it with what? Y over x. And then once you now do that, your final answer should be in terms of y and x. And then you have the solution to your differential equation. Yeah, so that's pretty much how it works. So with these two substitutions, you can be able to apply it and then solve your homogeneous equations. Now, in a case like this, you first of all have to confirm that it's not possible to make it separable as it is already from the beginning, right? So you have to try your possible means to see that it's not separable. Then you can now apply this. And once you make that substitution, once you replace that y term, you will see that you will now have a separable equation which you can now solve normally. Sorry, someone saying something? Someone say something? Okay. So yeah, that is what the case is for homogeneous equations. All right, so are there any questions so far?
I can't see your screen. I can't see it. Okay, I can see it now. Thank you, sir. So I will
That's sorry, Emmanuel, I can't. Your voice is breaking. You say you can't see
disconnected
my
when I
screen.
asked that question, sir.
Okay, sorry. What question did you ask?
I asked about that example
Okay, it's probably a network issue. Okay.
two. The example two under the
Example 2 is separable.
last slide before this homogeneous.
So we've looked at separable equations, we've looked at homogeneous equations. So the next thing we're going to be looking at now is, please mute your mic. Mute your mic. The next thing we're going to be looking at now is linear first order equations. So we are still looking at first order equations. But now we're looking at a different type of first order equations. And we're going to be looking at linear first order equations. They're called linear first order equations.
Ilé ìgbà ìsìn. Ìgbè gbọ́n. Want to give me cool now? The other night you talk about step. Please,
Please mute your mic.
please.
Kehinde, please mute your mic.
Why go? Look, okay, I'm not going
Please
to
mute your mic. What? Pastor, please mute your mic so that I don't get any noise from your end. All right. So for the linear first order equation, a linear differential equation is a differential equation where the dependent variable and its differential coefficients occur only in its first degree and are not multiplied together. Now, remember at the beginning I talked about dependent variable and independent variable, right? So I mentioned that the dependent variable is what? Y, and then the independent variable is X. So a linear differential equation is always dependent variable and its differential coefficients occur in its first degree. Now, what does that mean? Occur in the first degree means they are degree 1, which means that their power is only 1. And they are not multiplied together, so they are not multiplied. Now, this is the general form of the first order equation. So we have dependent variable, right? It's differential, y the x. Both of them are with the first degree, and they are not multiplying each other. Right? Y is multiplying with an x variable. This is multiplying nothing, and then we have another constant in the side. Now, if you have something that resembles this form, then what you have is a linear first order differential equation. And now, for solving linear equations, there is a different set of technique involved. And we introduce something that we call the integrating factor, right? The integrating factor, or IF for short. Now, for solving it, what are the rules to follow? We multiply through by an integrating factor, right? So we multiply the whole equation by this integrating factor. Now, how do we arrive at this integrating factor? Now, if you look at the general form of linear first order differential equation, we have the coefficient of the y term as p of x, or p of x simply means whatever is multiplying that y term, the function of x, right? So integrating factor is gotten by exponential integral of p of x dx. So basically, you integrate that p of x term, which is a function of x, and then you attach an exponential to that answer. When you solve that, you have your integrating factor. Now, with your integrating factor, you now multiply through by the d. Right? So, of course, it's going to involve a lot of calculations and legwork, but then this is the technique or the rules to follow to solve it. Now, let's take our first example that we have here, right? So, dy dx plus y equals exponential x. We see that it follows the general form for our linear dE, right? So, first thing we have to do is get our integrating factor. Now, if we come to the y term, what's the coefficient of the y term? Coefficient of y here is what? Is 1. Because there's nothing multiplying it, so the coefficient is 1. Now, having that our p of x is 1, we now do what? Solve. So exponential integral of 1. Integral of 1 is x, right? Of course, from our cheat sheet here. So, like I said, it's very important that you have something like this that you can always refer to where you see this common integral. So someone was asking earlier, the integral of exponential function. So we see here that integral of exponential u is exponential u. So it's the same thing. But for negative exponentials, that negative now comes down and you write the same thing. So of course, you use the chain rule to solve that, but then just know it's general that when you're integrating exponential function, your answer is always the same, right? And that's the same thing that applies now in this question we're about to solve, where we have an integrating factor that we're trying to find an integrating factor. So integral of 1 is what? X. Now we have exponential integral of 1, which will now be exponential x. So we know that our integrating factor is what? Exponential x. Fantastic. Now, what does the rule say? The rule says that we now multiply 2 by our integrating factor, right? We multiply through by integrating factor. Now, our integrating factor is what? E of x. Now, when you get that integrating factor and you multiply every single term that you have, so you're going to have what? E of x times dy dx plus y e of x is equal to e of x times e of x. That's going to be e of x squared, right? So now that you have multiplied through by integration, now why are we doing this? Because when you multiply through by your integrating factor, you can now be able to what? Factorize your equation. It's going to be possible for you to factorize your equation. And now this factorization is going to help you what? Make it separable. So once again, we're going back to our basics. Now it's important to know that when you do this, it will be possible for you to go back to separable because that's the only way where you can now find the solution. So the aim of all these, techniques and rules and steps is simply to come back to the most basic form of solving a differential equation, which is single equation plus b. It's yes to arriving at our answer. So once you do this, once you apply this integrating factor method, multiply through and then factorize, you will now see that it's possible for you to separate what you have left. Once you separate your equation, once you make it a separable equation, you can now integrate both sides and then get the solution to your differential equation. So it's not solved here actually to the end, but then I'm sure if you take out the time to do your solving and you should arrive at the answer that we have here. So I think it's possible to just illustrate this particular one. So for the purpose of this solving now, I will represent the y dx with y prime. So that it's easy for us to understand, right? So y prime times exponential x plus y exponential x is equal to exponential x squared, right? So now that I have multiplied through by your integrating factor, right? You now have to factorize. Okay, so in solving the linear first order equations, there's actually a very easy shortcut that we can actually use to arrive at our answer without having to go through the factorization process, because the factorization process involves some sort of manipulation, right? There's no straightforward method to arriving at that. So now, let me just illustrate the general form. So the general form is y, y prime. So I'm using y prime to indicate the y x plus p of x y is equal to q of x, right? Now, when you multiply through by your integrating factor, what are you going to have? We're going to have the integrating factor is if times y prime plus p of x y if is equal to exponential is equal to q of x times if, right? Now, when you now do your factorization and then try, and then finally your integration, your final simplification will bring you back to y. So this is like a shortcut or a general rule to apply, that your final after the factorization and cancelling out of things and manipulation, your final step would be y times if is equal to integral of so what am I going to use to represent integral now? Maybe that's true. So integral of the let's just that's the issue. Integral of q into if, of course, with c, which is your constant of integration. So this is like a very quick shortcut that will help you. Of course, this one now is going to be the x because the terms on this side is the x, and we are going to integrate. It's a very quick shortcut that is going to help you to apply the integration factor formula and solve it, and just go straight to getting your final answer, right? So normally, when you multiply through by this if, you don't have to collect like terms. So, for example, for an illustration, when you are doing a factorization of quadratic equation or something like that, so you have to collect the like terms. And your factorization. But there is a hack for it, right? So after writing this step, you can simply just skip to this next step. Now I use general form to represent it so that it's easier for you to understand, right? So y times the integrating factor is equal to integral of q of x, which is the constant term on the side, times the integrating factor of x plus c. And if we use it to solve this first example now to confirm that the answer we have here, we'll see that we'll have the same thing. Because, for example, if you take y now, what's the integrating factor? Our integrating factor is e of x, right? So y times e of x is equal to integral of e of x times e of x plus c, right? Now, when you integrate that and take the other e of x this side, you're going to have negative e of x. So let me just write it out for illustration. So y, our integrating factor is what? E of x, right? So exponential x, y times exponential x is equal to, what is our q of x? Our q of x is what? E of x as well. So e of x times e of x is going to give us e of x squared. So exponential x squared plus what? Plus c, right? So remember that we're going to integrate, we're going to take all the x to one side and then leave all the y alone. So if I divide both sides by exponential x, right? So if you divide this term by exponential x, if you cancel one of the exponential x here, and you have exponential x. If you divide this c by exponential x, you're going to have c over exponential x. Now, for exponentials, if you have over, so for example, if you have 1 over x, it can come up to be x to the power minus 1, right? So if you have 1 over exponential x, it can come up to be exponential minus x. So we'll now have y is equal to integral of, so integral, represent with that, of exponential x plus c exponential minus x, right? And we know from our calculus, our integration GT, that integral of exponential u, exponential anything is exponential u as well. So we can remove this integration sign and write that y, when we integrate it, obviously is equal to exponential x plus c exponential minus x, which is exactly the same thing that we have here. So it's good to keep in mind this shortcut, this hack, and then know that once you multiply by your integrating factor, your next result is going to be this, right? So that p of x then will disappear eventually after you do your factorization. So the same thing applies for this example. So the first thing, find the integrating factor. So here our integrating factor is what? First of all, the coefficient of our y is 2. Our integrating factor was exponential integral of that 2 times exponential integral of 2. Integral of 2 is 2x, so we have exponential 2x multiplied through. Then the next step you now write that like this. Let's simplify to get your final answer. So that's what solving a linear first order differential equation entails. Now the next form of equation we're going to be looking at is the Bernoulli equation. Now the Bernoulli equation is very similar to the linear equation, as you can see the general form here. So we have dy dx plus p of x times y is equal to q of x. Now the only difference is that for the Bernoulli equation, for the constant term on the right hand side, we have a y variable there, right? So we don't just have a constant in terms of x or an independent variable x. We have a dependent variable on that side too. So the form is almost the same as the linear equation, but then we have a slight difference. Now, to solve the equation, the first thing you have to do is, so we have a y term here, right? As you can see. So the first thing you have to do is what? Is to divide both sides by whatever that y term here is. So you divide through by y raised to the power n, right? Now, when you divide through by y raised to the power n, it means that you're going to have something like, so let's just write out where you're going to have, so I'm going to represent y, divide x to y prime again. Now, if I divide through this equation by y raised to the power n will cancel the y raised to the power n on the right hand side, and then I will not have to introduce over y raised to the power n on this side, or I can write it as y raised to the power minus n, right? So y raised to the power minus n times y prime, right, plus y raised to the power minus n times p of x y. Fantastic. And then on the left hand side, we're not going to have only what? Q of x, because we have eliminated the y raised to the power n. Now, having gotten to this point, what we're now going to do is to make a substitution. Yeah, again, we're going to make a substitution that's going to enable us change it to a linear form. All right. So the substitution we're going to make is that let z equal to y raised to the power minus n. It's getting complicated, right? But then follow me. We're going to see why we're doing this in just a minute. So we're going to say let z equal to y raised to the power minus n. Now, as usual, when we do our differentiation, when we do our substitution, we're going to get what? Dz dx, right? So we differentiate both sides, right, in terms of x. So if you differentiate both sides, well, we're going to have dz dx is equal to, then you also differentiate the right hand side with respect to x. So we're going to have So I represent z, differential of z with z prime. So z prime is equal to, so differentiating that part, this right hand side of this equation, you're going to have, so as we know from our differentiation, the power comes down and then you subtract 1 from the power, right? You're going to have 1 minus n times y raised to power. So 1 minus n minus 1, 1 minus 1 is 0, and then you're going to have minus n left. Then dy dx, which I'm going to represent with what? Y prime. Now, this is our dz dx. This is our z. Having gotten these two things, the next thing to do now is to replace our terms. So in your equation, anywhere that you see y, anywhere that you see y, you replace it. Anywhere you see y, you replace it with your value of z, right? So you substitute it in your original equation, and then you're not going to have an equation that is in terms of z now, no longer in terms of y. Now, why are we doing this? As usual, our aim is to make it into a form that we can already solve, right? So we already have a way for solving a linear equation. But now this Bernoulli equation is different, it's complicated because of this y raised by n that came in. So the point of this substitution now is to remove the y, right? Put in a z, and then by putting in that z, we can now make it in the form of a linear equation. Once we make it in the form of a linear equation, we solve it like a linear equation using the z. When we now finish solving it as a linear equation using the z, what do? You now do a back substitution. So we know that from the beginning, we said that z is equal to y raised by 1 minus n. So then we can now substitute back. Y will not be equal to z raised to power n minus 1. And then you now remove it. Remove that your z that you have now, and replace it to y, and you have your final answer. Right. So of course, as you go ahead, this gets more complicated because we're working with different or more complex forms of differential equations. But then these are the methods that are available to solving them. So you have pretty much no choice but try as much as possible to figure your way around it. But then it's good that you are aware of the various methods that we have for solving these differential equations, and you are able to apply them when the case arises. Right? So the floor is open now for questions. Gone just over an hour into the class. So before we come to an end, I'd like to take some questions. We have a few more slides remaining, but then I just want to throw the floor open to questions now so that we can tackle them before the class comes to an end. So if you have your questions, please, this floor is open. This is the time to go ahead and ask.
Sir, sir, sir.
Wonderful. I'm listening.
Okay, sir. Can you solve
Hello,
under the three
Emmanuel.
equation you have gave four equation that is homo. Sir, I'm hearing you, sir.
Okay, I couldn't hear you at some point, but I can hear you
Sir.
now.
Okay, thank you, sir. He gave four. He explained four slides. That is under the general introduction of the ordinary differentiation and homogeneous, and the equation of linear, and also this one that you currently dealing with, sir. Sir, what is the difference between four of them, sir, in solving equation?
Okay, so for all of these four equations, I showed you that. Please mute your mic. I'm getting an echo. I showed you their general form, right? There's a general representation that you can use to identify. So, for example, when you're taught quadratic equation, before they give you any quadratic equation, they showed you a general form. They showed you ax squared plus bx plus c equal to 0. So if you see anything that resembles, that's what a general form is. If you see something that resembles that, you know that, okay, this is a quadratic equation. I've seen this type of thing before. Now, each of them have their general form, right? Because, for example, for this linear equation now, I said from the beginning when I was explaining that, you know that an equation is linear when you have the y and the y, the x and y are of degree 1. So degree 1 means their power is 1, and then they are not multiplying each other. So when you have them like that, and you are seeing that it's written in this form, this dy dx plus p of x y equals q of x, you know that you have a linear equation. So that's how you identify it. Once you identify that it's linear, then you solve it like that. Now, the same thing applies to the Bernoulli equation. It has general form. General form is almost same thing with linear equation, but then you have y raised to power n on this other side multiplying it. So the idea for solving it now is to make this substitution so that it becomes like a linear equation, and then you solve it as a linear equation. And then when you're done, you now reverse what your substitution that you did. Now, for the separable equation and homogeneous equation, like I said, for separable equation, when you see a separable equation, you should know, because you can take all the x to one side and take all the y to one side. If you cannot, then it now becomes a homogeneous equation, and then you now have to now make this substitution y equals to v of vx, and to now turn it into an equation that you can separate. Once you can separate it, and you now solve it like a separable equation. So it's just to, and like I said, it's not something that you just get overnight. You have to solve questions as much as possible. So you familiarize yourself with how the formats in which they are presented. So when you see one, you know that, okay, this is this, and then you know how to go about solving it.
Equation, please, throw more light a bit, sir. I'm almost
I didn't get your question.
homogeneous equation. I have understood it, but throw more small light there, sir.
Okay, so for the homogeneous equations, so what we are looking at here now is you see an equation that you have in terms of y and you have in terms of x. So you have the numerator. So how you identify in the homogeneous equation, you normally have the numerator part and you have the denominator part, right? So here we have x plus y over x minus y. So this is the numerator part, the denominator part. The numerator has x and y in it. The denominator has x and y in it. Now, you cannot make this a separable equation. It is not possible, right? You have tried. And of course, if you try, you will see that it's not possible for you to get all the x to one side and to get all the y to one side. It's not just possible. Now, what do? You use a substitution. The substitution you're going to use is y equal to vx, right? And then you now do dy dx. So when you do dy dx, you get v plus x dv dx. Now, what the substitution is going to do for you is that it's going to turn this into an equation that you can now later separate. So when you now see y, anywhere you see y, you put vx. Anywhere you see dy dx, you put v plus x dv dx. So your new equation now is going to be in terms of v and x, right? It's going to be in terms of v and x. Now, that new equation that you're going to get is going to be separable, right? You're going to be able to turn that one into a separable equation. Once you're able to separate it, right, in terms of v and x, now you no longer have y because you have substituted your y away. Once you have v and x, right, you can now integrate. You make it separable. Take all the v to one side, take all the x to one side, and then you now integrate. Once you now integrate, you get your final answer. Your final answer is going to still have v and x. Now, but you don't want v and x because v was just a random variable introduced. Your original question was y and x. You now what? Reverse to substitution. So anyway you see v, what do you now put? V from here now, v is what? Y over x. Anyway you see v, you now put y over x. And then you now have a final equation that is only in terms of y and only in terms of x. So yeah, that's pretty much how homogeneous equations work. So I don't know if I've been able to answer your question.
Okay.
So I think at this point we'll draw the curtains for today's class for 11. Yeah, so we've been able to explain differential equations and showing the different methods of solving the first order differential equations. The rest of the slides have the explanation for second order differential equations. Unfortunately, I don't think I have the time to get into that right now. So, but then the slides I think will also be made available, so you can just look through it as well and get an idea of how the solving of second order differential equation works. But we've covered every single type of first order equation you can come across and how you can approach each of them to solve it. So yeah, we'll draw the content at this point. Thank you for making the time to come to attend the classes, and yeah, have a wonderful night first. Good night.